In the introductory video for this module, I mentioned that plants make sugars that can be stored for energy or used for structural components in building cell walls, components like cellulose, hemicellulose. These simple sugars are made from photosynthesis and are accumulated in these new forms, starch or the structural components. And this accumulation is what we'll refer to as polymers, or in this case of sugar, polysaccharides. Poly meaning many, saccharides, sugar. And I would like for us to just take an example and see how this process, the chemistry of this process. So here we have two glucose molecules. There's glucose and another glucose molecule. And the way this combine is through dehydration. So we have this hydrogen from one of the molecules and then hydroxyl from one of the molecules are removed. And so we have a structure like this. Dehydration reaction is a condensation reaction. And so this is what we'll call a disaccharide. And we can have many more of these combinations. So we are having more than two units. We can have several units, and when the units are less than 20, we'll call them oligomers, and greater, we'll call them polysaccharides. The definition of oligomer is kind of disputable. Some people like to define it as up to 10 units, but I like to go with the 20 units. So this is how we form those polymers, those structures. The orientation would differ. I don't have the diagram here, but when you're looking at starch, which is made from simple glucose unit, and cellulose, starch is easily degraded compared to cellulose. The structure of cellulose, the orientation of the sugar units are different. We have interchanging bonds. But we'll just look at this very simple unit just for explanation's sake. So the question is, if we know that these polysaccharides are formed in the plant by removing water molecules or dehydration, what will we do if we're interested in getting the simple fundamental units? So in the introductory video, I said this module will be looking at the simple fundamental units, and this partly because most of the reactions for biofuel production starts with the simple units. So if we have polysaccharides like starch or cellulose and want to get the simple units, what do you think we'll do? Yeah, I guess you will think of add water because water was removed, or maybe you say we need water, and you're right, and that's the basis of hydrolysis. So in hydrolysis, we're using water to break up the bonds, and then we incorporate water, breaks up the bond, and then gets incorporated into the structure. So we would take a look at it in a little while. So here's the disaccharide let's say we formed in our previous slide. So what we do is that we add water, and water kind of push away these two structures, these two units. We'll have our two glucose units, and then the one hydrogen joins with this oxygen, and then it's separated. One hydrogen join, and then the other hydroxyl group joins the other glucose. So we get our simple unit back. So this process is the opposite of dehydration. So basically we'll call it hydration. So hydrolysis is a kind of hydration reaction. We use water, like I said, the definition of hydrolysis. I use water to break up the structure, and you're incorporating the water molecules into the structure. So there are several other reactions that we can consider for biofuel production. Generally, methane production from anaerobic digestion or ethanol production from fermentation are what most people are familiar with. The fermentation process sounds very simple, but it is complex. It's a very complex process with several reactions that lead to the end product. In this case, I'm referring to ethanol. And some of these reactions can include phosphorylation, isomerization, oxidation. We can have dehydrogenation, dehydration. So several reactions in all to convert sugar, glucose to ethanol. You might be looking at some 10 to 12 reactions. These reactions are not most times when we are representing this, we just look at one equation. We have our sugar and then we have the end product, glucose and CO2. But like I said, there are a lot of things that go into that production. Today we're going to look at some few other biofuel production reactions. I have a table here, and we have dehydration, we have hydrogenation. The definitions are here. Hydrogenolysis, decarbonylation, hydroxygenation. I'm not going to go through all of them, but you can pause this video to look at the names, and then there's a very brief definition, just the basic explanation of what is involved in these reactions. And of course, there are a lot more reactions than this. But these are what I want us to look at. We're not going to go through all of them, but we'll look at a few of them. So let's say you want to convert this simple sugar, this glucose, this glucose, to alkane, and we are thinking of hexane, and we are looking at alkane because this is a carbon-rich fuel. It has high energy density, and if we look at gasoline, you see that gasoline is mainly composed of alkane compounds, and so if we want to produce drop-in fuels or high-density fuels, we'll be looking at alkanes or mainly alkanes. So we'll use that for example. So what will you do if you want to produce hexane from glucose? I want you to think about it a bit, especially if you've taken a look at these definitions. What do you think you'll do? What are some of the processes that come to your mind? So basically would be adding, we have 12 hydrogen here, we have 6 carbon, so we're not doing anything to the carbon. We have 12 hydrogen, we have 14 hydrogens, so basically we'll be adding 2 hydrogens here to get 14. And we'll be removing all of this oxygen. So the hydrogen, adding 2 hydrogen will be hydrogenation. Possibly there could be other reactions you could use, and then to remove oxygen, deoxygenation. And again, deoxygenation is just a broad theme. There could be different ways different ways of removing this hydrogen. So if we look at table 1, anyway, I'm not going back to that table. If you looked at that table, you would find out that there's a reaction, hydroxygenation. Let's see whether we can go back. Okay, so that's this. And hydroxygenation is you're using hydrogen to split up the CO bonds. A CO bond, you're using hydrogen to split up the CO bond, and in the process removing oxygen from the compound. So that seems to satisfy the two goals we would have in mind, because we want to add hydrogen. We use hydrogen to split it up. Hydrogen become part of the compound. At the same time, it's removing oxygen. So this seems like a very good, ideal reaction to use. So I have a little flowchart here, and I've tried to look at some common ways which people have tested in lab and have tested on commercial level, demonstration level, in producing alkanes or biogasoline. So you can have two processes. You can have the biochemical process or chemical process. Sorry, I can't find my cursor. So this could be biochemical or chemical, depending on how your hydrolysis is performed and how your pretreatment is performed. We can have biological pretreatment, we can have enzymatic hydrolysis, we can have chemical pretreatment, we can have chemical or acid hydrolysis. So this can be a biochemical or a chemical process, and then we have a thermochemical process here, gasification. So we'll go through them. In this process, we have simple sugars converted to alcohol, and then we have hexane. So we see the process here. We have hydrogenation, dehydration, deoxygenation. Or we can go through this route: dehydration, then deoxygenation to go to our alkanes, or depending on how much hydrogen is available or supplied to the reaction, we can be produced another kind of liquid fuel, the methyl fura, which is currently additive, gasoline additive, but can also be used as a drop-in fuel, added at higher levels as drop-in fuels. Or during pretreatment, we can have organic acid produced, chemical pretreatment, and you can go through this route: the hydrogenation, get your alcohol, you dehydrate your alcohol, get alkane, hydrogenation, get an alkane, and you can couple to get longer chains. Now if we go through the gasification route, we'll produce syngas, and then we can go through Fischer-Tropsch synthesis, and we can have various range of hydrocarbons. The Fischer-Tropsch synthesis usually involve multi-reactions. Several reactions are taking place in this under this corporate name, and they could include hydrogenation of the carbon monoxide, or hydrogenolysis of the CO bonds. You can have coupling and several other reactions. So this is just a simplified version, but like I said, many reactions are taking place in the Fischer-Tropsch process, and they will come up depending on the catalyst. You have different range of fuel. You can have jet fuel, you can have kerosene, you can have petroleum grade fuel. All will depend on the catalyst you're using. So now let's look at, I just want to expand this. I have the formulas here, but I'll just expand them and we'll look at the process a little bit more. So if we want sugar to hexane, this is the stoichiometry. We convert sugar to an alcohol phase, sorbitol, through hydrogenation. Sorbitol is converted to hydroxymethylfuran by dehydration, and the hydroxymethylfuran is converted to hexane by hydrogen oxygenation. Now again, just as in the fermentation process, this is a very simplified way. Between this process, conversion of sorbitol to hexane, you can have maybe 6 to 8 reactions. So a series of hydrations and hydrogenation or hydroxygenation. So that's a series of reactions, taking place. You're adding, removing water, adding hydrogen. But this is just very simple in these 2 steps here to get our hexane. And this is our compound of interest here, hexane. So that's just looking at this first pathway, and then we can look at this other pathway. And in this pathway, we convert glucose to hydroxy methylfurfural through a dehydration process, and then we hydrodeoxygenate furfural to get hexane. So it looks very straightforward. And again, there are a lot of series of reactions that will be taking place before we get. But most of these reactions are basically dehydration, hydrogenation, and reactions taking place. And then we can look at this pathway. But I've said that for the sugar pathway, there are several pathways. You can convert the glucose to organic acids and then go on from there. So there are several pathways this can take, but most of those pathways involve this processes: hydrogenation, dehydration, or hydrodeoxygenation. So they're very similar reactions, but starting from different with different starting reactions. Let me put it that way. So now we'll look at organic acid, and we're using acetyl. We convert acetyl to ethanol through hydrodeoxygenation. We use hydrogen to remove the oxygen. We're incorporating some of the hydrogen into the acetic acid. Then we'll convert hydrogen to ethane through dehydration. We'll remove water. You can also add the water here. I like to put it here just to, or you can write your equation plus water, but I love to write it this way. And then you can convert the ethane, which is a unsaturated hydrocarbon with double bonds. You can convert it to ethane through hydrogenation to saturate it. As you add more hydrogen, that's you remove the double bond and get it saturated. And then there are several coupling reactions, because if you look at what do they call it, gasoline, we're thinking of carbon in the range of 4 or 5 to 12. So we would need to increase the chain length, if we start with acetic acid. And these have some coupling reaction. We have oligomerization, we have oxidative coupling, and this partial oxygenated, we're using an oxygenated compound, not oxygen, and this in this case is ethanol, to react with ethane to get hexane. So all these, I'm just looking at hexane, ethane reacting with oxygen to give you hexane and water, or ethane reacting with what do they call it, ethanol, to give you hexane and water. So yeah, so these are a few of coupling reactions. There are several ways one can couple these reactions. Again, these reactions are very simplified. Generally they would involve, like I said, hydration, hydrogenation, or in some cases dehydrogenation, hydroxygenation or deoxygenation, hydrogenolysis. Of course, we know that hydroxygenation is a form of hydrogenolysis. So we can look at these things, and like I said, most of them, the way I've presented is just very straightforward. Most of them will involve a lot of reactions to get your final product. But in all, these reactions, most of these reactions have high activation energy, so you need catalyst, and you have to get appropriate catalyst, and it may require addition of heat or pressure, or both of them. That's heat and pressure. The catalyst is very important. The kind of catalyst you use is very important, because that will determine your outcome, your product. Just like I mentioned, the Fischer-Tropsch process, depending what catalyst, you could be producing jet grade, diesel grade, or gasoline grade fuels. And even with these processes, in producing this example with simple alkane, the catalyst is important. And in some cases, you might consider manipulating or changing the functional group, because if you've done the reading, you would realize that reactions can be based on functional group, and so compounds with similar functional group will participate in some particular kinds of reaction and may not be able to participate in some kinds of reaction. So sometimes in manipulating our chemicals or basic biomass units to get the fuel we want, you might consider manipulating or changing the functional group to allow these otherwise impossible reactions to take place. And something this is called functional group interconversion. And in some cases, you might have to change the structural arrangement. That's isomerism. And this isomerism, we see it in ethanol fermentation. Like I said, we don't see all those processes reflected, but when you go through the processes that takes place in the cell wall to give you ethanol, microbial cell wall, you find out that there's some form of isomerism where glucose is changed to fructose. And so when you think about fuels and you think of you are very innovative, you're thinking like, what can I do? Is there something I can do? These are options you have. So we'll look at, we're not forgetting our oils, because we said sometimes plants can produce oil as a form of energy storage. And I will not go into detail with this, but I just want to point out that we have green diesel and biodiesel. Green diesel is also known as renewable diesel, and the difference in these two is more about the process in which they are made. So when we look at green diesel, we are using some of these reactions I just mentioned, where your plant oil or bio oil, I'm talking about oils produced from the biomass plant through processing, either pyrolytic processing or any other kind of processing. And plant oil is the oil originally in the plant that we can extract. Sorry, pyrolytic. Yeah, so plant oil or bio oil can be upgraded from a less compactable form. When I'm using compactable, I'm comparing it to to conventional diesel. So you can upgrade these bio oils or plant oils to be from less comparable fuels to a more compactable and more comparable fuel. And so the less comparable is will be the biodiesel. Biodiesel is produced through transesterification, and which is more like an exchange of functional groups. And but we produce green diesel, and we use basically it's more like hydro deoxygenation, where we remove some oxygen and incorporate more hydrogen to increase the energy density and the carbon and relatively the carbon content. So like I said, there are so many ways one can look at this fuel production. Of course, one setback is the high cost, especially when we look at hydrogenation. There doesn't seem to be a very, very economical way of producing hydrogen. So that step can be very expensive, and most of these other steps too can be expensive. So it's a major setback, but that doesn't prevent one from looking at possible pathways to produce fuels that are more compatible with current system or are more energy dense. And I'm hoping that with this briefing in organic chemistry, your appetite will be your innovative appetite for production would be stirred up. So that'll be it for now, and I hope to have another conversation with you soon. Have a great day. Bye.